On to question 6 then. And at first glance, this looks suspiciously like a gas laws question. And part A, defining pressure. Pressure doesn't have a sort of wordy definition. It is just force divided by area. I don't know of any other sort of sentence or whatever that is used to define it. Do bear in mind when you're asked for a definition, and if that definition is just the product or something like that of two other quantities, you can't just write the letters. You have to write it in words. You can write the letters if you then define each of the letters, which is, so it's quicker to write the words. Okay. Part B, a sealed canister contains 0.2 moles of oxygen, and we're given the RMM there. An identical canister, so identical canister implies the same volume, has the same number of moles of nitrogen, and we're given the RMM of nitrogen at the same temperature. Giving reasoning, determine these ratios. So pressure of oxygen divided by pressure of nitrogen. We're going to want to use the ideal gas law to answer this. So PV equals nRT is what we're going to use. And therefore I can write that expression as PO over Pn must be equal to number of moles oxygen or temperature of oxygen divided by volume of oxygen all over, that's supposed to be like a subscript, and I've not drawn that very well at all, have I? There we go. Over the number of moles of nitrogen times the gas constant times the temperature of the nitrogen divided by volume of nitrogen, but and V T are the same for both gases. Both at the same temperature, both got the same volume, both got the same number of moles. Therefore, P oxygen over P nitrogen equals 1. RMS speed then, there's so many different variations of essentially this equation that it can be useful to just make sure you're using the most convenient one. I've got the formula sheet on the right hand side. Hopefully you can kind of see that well enough. For the purposes of this question, given that we know the RMM, we know the number of moles, we know the volume, we've got information about pressure and temperature, and we're trying to find RMS speed. That is the version that I would use. So I would be using P equals 1/3 N over V times C bar squared. And I'm just going to rearrange that into an expression for C bar, and then hopefully that's going to fall out with some sort of answer. So C bar squared, rearranging for that, is going to be 3PV over NM. Therefore, C bar oxygen over C bar nitrogen is going to be equal to the square root. Don't forget the squared. Square root of 3P oxygen V oxygen over N oxygen M oxygen divided by 3P N V N N M, and it's a lot of subscripts. But as before, P, V, N are the same for both gases. Same number of molecules. Don't forget capital N is the number of molecules. But of course, number of moles translates directly to number of particles. Therefore, CO bar over n bar is equal to square root of 1 over m naught, m0, sorry, m0, mo, oxygen, dearie me, divided by 1 over n, which equals to the square root of n over mo. So that is equal to the square root of 28 over 32. That's a job for the calculator. 7 over 8 square root is equal to 0.935. I've probably put more steps into that than is absolutely necessary for 2 marks. But that's the method. You could probably get away with abbreviating that a little bit. You probably don't actually have to write out this full substitution. You could probably just spot that since those are all the same for both gases, then c bar squared is proportional to 1 over m. Would have saved you actually quite a lot of writing. So I should have done that, but I didn't. Okay, center of the sun, we're given pressure, we're given density. Calculate the RMS speed. So again, it's always worth just, because there will be a long way to this, and often there's a short way to it if you're using the most appropriate form of gas law. So the equation that I would use this time would be, would be this one: pressure equals 1/3 rho c bar squared. Where rho is the density. And then just rearranging for c bar, it's 3 times pressure over density. Don't forget to square root because we're after the RMS speed, not the RMS speed squared. Substitute and solve. Sorry about my sloppy handwriting here. 1.6. I think my pen's got narrower or something, looks a bit scratchy. I must have selected a different pen. And into the calculator, and 684653, so 685,000 meters per second. Pretty rapid, but we are talking about the center of the sun here. So finally, state 2 reasons why the ideal gas kinetic theory is not likely to give accurate results in this case. Not likely. So if we think about our sort of ideal gas and the assumptions that we make for that, those assumptions are that the particles themselves take up negligible volume, that there are no forces between the particles, that collisions are elastic. What else have I missed? And that the gas is monoatomic, I suppose. So are these valid assumptions? We're only after 2 that aren't valid. Arguably, all of those are invalid in the center of the sun. So any 2 that you like really is going to be fine. So there will be, remember the center of the sun is a plasma. It's a ridiculously high temperature. So it is fully ionized gas. So what we've actually got in there are mostly just protons and electrons. So the particles are charged, and therefore there will be forces between particles. So there are forces between them when they're not in collision, is my first point. And secondly, given how high this density is, you could argue that the particles themselves actually occupy a non-negligible amount of space. You know, in a normal gas, the particles occupy a tiny, tiny fraction of the volume. Does occupy have, oh, it definitely doesn't have 2 P's, I'll tell you that. It does have 2 C's, doesn't it? Particles occupy non-negligible volume. I think we'll do it. The other points you could make are the particles aren't all the same. Protons have a radically different mass than electrons, and therefore they'll be traveling at very different speeds indeed. The other thing you might mention is at such a high temperature, collisions happening between these are charged particles. So if you think back to the particle stuff that you've done, the interactions between them would be electromagnetic, so collisions between them are likely to produce photons and therefore not be elastic. So really it's any of the ideal gas assumptions you could counter here, but it says state 2 and we have stated 2. That's it.